All right, my friends, let's get started. For L'Hopital's rule, please remember that you'd need to have a certain condition met. And that is, first of all, that you have a limit of the form. Limit as x approaches c of one function of x divided by another one, or at least something that could be manipulated into that form. And if your limit then is an indeterminate form, then the conclusion would be that the limit as x approaches c of f of x over g of x is the same as the limit as x approaches c of f prime of x over g prime of x. There we go. Okay, now for the graphs, I've got the xy planes already pre-done. Do know, unless marked otherwise, the tick marks are each worth just 1 unit. Okay, so for 77, please remember that natural log of x is really just a logarithm with e as the base. So those two things are the same. Anyway, so the three numbers that you would plug in if you're t-tabling this out for x would be e, 1, and 1 over e. So if x was e, then this would be asking e to what power equals e. The answer would be 1. And remember, e is about 2.7 or just shy of 3. So you put e in, you get 1 out. If you put 1 in, it's asking e to what power is 1. The answer is 0. If you put 1 over e in, it's asking e to what power is 1 over e, and the answer is -1. And then really it's these 3 points, as long as you know the shape that a logarithm has, that it has kind of a slow growth side, and then it has this vertical asymptote side as well, then you should be good with those 3 points of accuracy. So let me fix that just a little bit there. Oh my goodness. All right, there will be no fixing that, I guess. There we go. Teacher trick, just make everything globbier. Everything should be fine. Okay, now let's move on to the tangent graph. Let's see. So tangent of 0 is 0. Tangent of pi over 4 is 1. Tangent of pi over 2 is undefined. Tangent of, sorry, negative pi over 4 is -1, and tangent of negative pi over 2 is undefined. So, and then tangent kind of looks somewhat like an x cubed graph that just keeps repeating itself. So anyway, you could kind of just continue that pattern as you continue out. Okay, now before we go too much farther, I do want to make sure that you kind of know the reason I'm having you review these graphs. Okay, so like for example, look back at the logarithm, the natural log graph, number 77 there. So for that graph, you might be asked questions inside of a bigger problem very soon. You might need to know, what's the limit as x approaches infinity of the natural log of x? And the answer to that would be infinity. It's a slow growth infinity, but it's still infinity. You might also be asked, instead of that, you might be asked, what's the limit as x approaches 0 from the right of the natural log of x? And hopefully it makes sense. According to this graph, the answer would be negative infinity. And so the reason I'm having you review these graphs is because I feel like that's the quickest way to access this information that you're going to need when you're in the middle of a bigger calculus problem. A question that you could be asked about the tangent graph would be something like, what's the limit as x approaches pi over 2 from the left of tangent of x? And hopefully it makes sense. The answer would be positive infinity. And then how would this change if instead it said limit as x approaches pi over 2 from the right? And I hope it makes sense. The answer would then be negative infinity. So, and it's these graphs that should make these limit questions go pretty quickly. So, all right, now let's transition from the tangent graph to arctangent. Remember that to get from the graph of a function to its inverse, you just swap the roles of x and y. And so we're going to focus on just swapping the roles of x and y on this main, let's say that on this primary cycle of tangent over here. And so let's start with the asymptote. So this asymptote on the right on the tangent graph has the equation x equals pi over 2. If you swap the roles of x and y on that, you get y equals pi over 2. So on the arctangent graph, that turns into this horizontal asymptote at y equals pi over 2. And then similarly, on the graph of tangent, you have a vertical asymptote at x equals pi over 2. So on the graph of its inverse, you'd have a horizontal asymptote at y equals negative pi over 2. And then from there, you could just keep swapping the rows of x and y and do it point by point. So the point 0, 0 on tangent would become 0, 0 on arctangent. The point pi over 4, 1 would become 1 pi over 4. And then negative pi over 4, negative 1 would become negative 1, negative pi over 4. And then you could use the idea of things needing to be reflections in the line y equals x to finish the graph of arctangent there. Anyway, and I hope it makes sense. We won't be doing the work that I just did on the other cycles of tangent because then arctangent wouldn't have been a function. And so there you go. Now this is going to be a graph that comes up quite a bit, okay, in our future work. And so, for example, let's see if I can move this over a little bit. No, I can't. Okay. For example, you will likely be asked, what's the limit as x approaches infinity of arctangent? And so hopefully it makes sense according to this graph. The answer would be pi over 2. And then similarly, what would the limit as x approaches negative infinity be of arctangent? And I hope it makes sense. The answer to that would be negative pi over 2 if you just look at the graph and think about the limit question that you're being asked. So hopefully you guys are doing fine with this. Anyway, so problem 80, or formula 80, graphing e to the x, just drop in negative 1, 0, and 1 for x and then see what you get and connect the dots essentially. So e to the 0 is 1, e to the 1 is approximately 2.718, aka just shy of 3. And then e to the negative 1 would be 1 over e, which is roughly, something between a half and a third. So I usually put my dot, a smidge higher than a third and call it a day. There you go. Anyway, and then you'd have a fast growth side on exponential functions and then a horizontal asymptote. So for this one, you might be asked, what's the limit as x approaches maybe negative infinity of e to the x? And hopefully it makes sense that the answer would be 0. If you were asked what's the limit as x approaches positive infinity of e to the x, the answer would be infinity, and a very fast growth infinity at that. Okay. Let me take this little cloud off over here. Okay, f of x equals e to the negative x. Same thing, just plug in 0, 1, and negative 1. If x was a negative 1, you'd actually get e out here. If x was 0, you'd get 1. And if x was positive 1, you'd get 1 over e. So this graph has a fast growth on the left side. And then it has a horizontal asymptote on the right side. Okay, and just think about, for this one, what would you say if someone said what's the limit as x approaches either positive or negative infinity on this graph? Okay, let's see. Graphing f of x equals 1 over x. I just put in, x values. So put 1 in, put 2 in, put 1/2 in. Imagine putting 3, 4, 5, or 1/3, 1/4, 1/5 in, and you should feel pretty good about getting this side. Don't forget to put some negatives in. So put negative 1 in, put negative 2 in, put negative 1/2 in, etc. So for this one, you might be asked, what's the limit as x approaches infinity of 1 over x? The answer, my friends, would be 0. You might be asked what's the limit as x approaches 0 from the right of 1 over x. And hopefully visually it makes sense. The answer would be positive infinity. If you're asked what's the limit as x approaches 0 from the left, you would get negative infinity. So those are the common questions that you'd be asked about this function. Okay, last one, f of x equaling 1 over x squared. So let's put 1 in, you get 1 out, put 2 in, you get a 4th out, put 1/2 in, you would get 4 out. Let's put some negatives in, put negative 1 in, you'd get 1 out, put negative 2 in, you'd get positive 1/4 out, and put negative 1/2 in, and you'd get 4 out again. There we go. Something along those lines. Anyway, so hopefully you feel comfortable with those graphs. It is going to be a very good idea for you to be familiar with them as we move into the new unit here. You'll see why very, very soon, I think. Anyway, so let's get started. Section 7.8 is called improper integrals. I'll break this into 2 days. To get started, for example 1, I'd like for you to sketch the region whose area is described by each improper integral. For part A, the integral is from 1 to infinity of dx over x. And for part B, the integral is from 0 to infinity of e to the negative x dx. Okay, go ahead and sketch the region whose area is described by each improper integral and see if you can figure out what's so improper about these integrals. All right, see how it goes. Check in with me in the next video.